Hi, and welcome back. Thanks for joining me in this segment about best practices when you're building Fyne applications. We're going to talk about how you can keep clear and maintainable code from the beginning of your project all of the way through so that your graphical application can stay clean and easy to work with through the life of it and not rot along the way, which sadly too many projects are accustomed to. Let's start right at the beginning with your project setup. Now, apologies to people who are joining us with a lot of Go experience or have built lots of applications in the past, but I thought it would be useful just to start from the very basics. And the very basic is make sure you have source control set up. I think that Git is pretty much ubiquitous in terms of setup for Go projects, and it would certainly be recommended. Not only do you want to initialize your source control or your Git repository, but you want really to figure out where it's going to be hosted, because that's going to help a lot a little bit down the road when you figure out which bits of it you want to share, who you want to give access to. So if you're setting it up on GitHub or GitLab, then this would be a good time to do it, because that's going to lead directly into your module name. If you can use a namespace that is globally unique, then a lot of things get easier when it comes to sharing later on. And if you have source control on a centralized system like GitHub, this is an opportunity to put it in your module name. And if you've issued many go get commands yourself, you'll know that this feeds into how things are discovered, installed in your Go path and module caches. So getting it right from the beginning makes things a lot easier. I would also recommend taking this opportunity to install some of the standard tooling that is available to keep your code in good shape. GoFmt or Go imports or newer versions are available. Definitely a good place to start, making sure that your code is in a standard format and doesn't make potential mistakes of white spacing or misleading indentation. And Go vet, although available in the standard Go tool, is a really helpful thing that you should run fairly regularly to make sure that you're not making other common mistakes in your code. If you don't know Go imports, you can go get it from this URL here. That's the one that I use mostly, and we've had a lot of good success keeping everything organized, following their rules. I would also recommend setting up a static checker. One is available at the URL there, highly recommended, and that is going to perform static analysis on your code. So it can look at your source code and figure out if there are harder to see problems with what you've written. It might be that you've accidentally included a security vulnerability, or you're using variables in a way that's not obvious from your code. It's going to be able to say, we think there's a possible mistake here. So adding to what GoVet can do and making a lot more checks to ensure good code going forward. This last one, perhaps not something that everybody agrees, but I think it's really helpful to have a complexity check against your code as well. So I would recommend GoGet for GoCyclo. Now that is going to check on your application code that no methods are getting hugely complicated, and so everything is essentially supposed to be more readable. It's making sure that your methods don't get too long, have too much indentation, and so you don't accidentally start doing too many things in one place. So that's your tooling setup, and the Go module file that you see illustrated there is probably a good place to start. You have your namespace, a reasonably up-to-date Go version number, and of course you'll have installed you'll have installed Fyne v2, which 2.2.3 was pretty recent when we recorded this presentation. You're set up and ready to go. But if you have an opportunity, you can automate some of these checks as well. So instead of having to remember to run the tools or asking other people who start work on your tools, you can set up these hooks and automations that will help. Git provides the ability to have all sorts of hooks on various different stages in the project lifecycle. I would recommend looking at pre-commit. This is a hook that's going to run each time you're about to send some code out to GitHub or to your collaborators. It is configured locally per clone, so this is not something that's going to be sent out to the repository and forced on everybody that you're working with. But nonetheless, I think it's a really good idea, and I end up copying my Git hook across all the repositories I have. I've included here a perhaps complicated looking hook, but I find it really helpful. You can see an example of this in the Fyne contributors documentation. Essentially, it is running through format, test, vet, lint, and cyclomatic complexity, one step at a time, and if the command matched to that label fails, then it stops and outputs an error message into your console. So this is going to run locally each time you're thinking about committing that code. Even better is to have it on the remote system as well, so that you don't have accidental configuration improvements on your system make a difference on whether something passes or not. So like I said, if you're on GitHub or GitLab, there's the opportunity to use hooks on the pull request cycle perhaps. And so you can run things like vet, format, and static check on their infrastructure, which means it's free of the biases of your local computer. And you can run the unit testing that you'll have set up as well. We'll talk more about that in a moment. And it's a good idea, if possible, to make sure that's running on different operating systems and possibly different versions of the Go compiler as well. I haven't included examples about how to do that here because it's going to vary based on platform and possibly over time much more than the local tooling will. And while you're setting that up, it's a great idea to report on code coverage as well. That is, how much of your source code is tested by one of your automated unit tests. There's a lot of tools out there as well that work in this area. We use Coveralls, which has got a good report and hooks into the GitHub flow that I use in most of my projects. So we have our project set up, we're using all of the best tools to make sure that our code is clean, and we are enforcing that through automation on our remote service as well. So we can see that everything is as healthy as it should be as we add code. But we haven't really added any code yet. So let's move on. And I thought it'd be really interesting to talk about packages. People coming to Go and also to Fyne are often feeling that they don't have the right package set up. Which directories should there be here? Are they putting everything in the right place? Well, the super secret thing here is actually don't add any packages too soon. If you don't know why you want a package or whether you need one, then you probably don't. So I wouldn't worry too much about it. The one thing that then leads you to is your main package should be at the project root. Simple, you have one package, it's the only directory. And so you would then have the Go module file that we showed before and your first Go file, main.go, in the current directory, which is the root of your project. This means it's really easy for people to discover and build your application. They don't need to know or to figure out which subdirectory it's in, where in the tree they might find relevant information. It is possible, and I understand that people don't necessarily like this because other files might appear at your project root. README files, configuration for other things. But if you're keeping it just to these three files, which we will do, there's not too much worry about that. And it's your entry point, it's not the bulk of your application logic. The next thing that we might want to add is an internal package. That's going to allow you to keep code separated so that you've got a good separation of concerns between your main code and other items like the calculation logic that you might have in your app, and grouped by area of application such as logic. And anything in internal won't be discoverable or accessible by external systems, so your only entry point is the main package and the main file that we created already. Now that we've started to gather code in our project, we want to make sure that the graphical user interface files are separate from the rest of the application. This might seem a little bit difficult to do, but we'll cover some strategies there. Primarily though, by keeping these separate, you can focus on an API for your application that is clean and easy to understand, and the user interface, which is a simplistic way of presenting that to the end user. It's another way to ensure separation of concerns and a cleaner API by having these items separated. If you put it all together, you're able to break certain assumptions, files get bigger, and actually untangling it later is much harder. We recommend also, as illustrated there, one file for each area of your application. So the definition of area is going to vary based on different systems, but perhaps it's related to a screen. So you might have a search screen and a welcome or landing screen. You may also choose to put certain complicated dialogues into a separate file. It's up to you. Just make something here that is understandable by people who are joining into your project. At this stage, we have some files, pretty clear of their usage. I wanted to talk just a little bit about the structure of your code itself. I've entitled this Small Files, Small Functions, Clean Code. This might resonate with anybody who's seen the work of Uncle Bob Martin and his Clean Coders book, video series, and website. He has a lot of great things to say about how to organize your code, how to keep things simple and clean. And so we showed before, multiple files with clear names is going to make it easier for people to get into your project and understand how to start contributing early on. And that's not just useful for open source projects, but it could be really great for anybody onboarding into your team, having come from somewhere else, or into your company. And any helpers you can give them along the way is really important. If possible, try to keep to one main type for each of these files. So an area of the application might have its logic in the search type, which can be interacted from other areas. It's not necessary, but as you can imagine, that means that you can define the functionality related to search at a level that could be discovered and presented in your development environment, rather than trolled through in a massive file for somebody trying to find the right thing. And at that time, whilst keeping things small and simple, the clean coders tell us that functions should be really simple. They should have one main purpose. This is sometimes difficult to really understand how to, in a large application, keep it simple. But if you keep to that mantra, then the function names will be quite helpful. Each function is only going to do one thing, so its name is going to tell you what it does, and you don't now need to look 3 levels deep in complex logic to understand what's going on. And in having one main purpose, remember also a function would need to be a getter or a setter or a logic of some sort. So you can see from the signature whether it is receiving information and processing it, returning information, or setting it through some sensible name. So a lot of hints can be conveyed through simple, short methods with well-picked names. And although I said it before, this applies also to user interfaces. A big complex screen might feel like it's one piece of functionality, but it's made up of so many different pieces. It's better to split that up into small sections, and the function that perhaps builds the screen that you're talking about is really calling into lots of different smaller functions that come together to create the user interface and the functionality that you want. So thanks very much, Uncle Bob, there, for your recommendations, and do check out the website or his book if you haven't done before. He would also tell you, of course, unit testing is tremendously important. I completely agree. I don't want to step through how to write lots of different unit tests, but suffice to say that the design that Go promotes for good testability follows through into the design of Fyne. A graphical widget or component can be tested just as easily as any other part of your application. As we illustrate in this example here, we're wanting to write a test that tests the selected text of a widget. So we create a test called test text selected, and in there we create a new entry widget. We use the test utility package that's been imported above from fyne.io/fyne/v2/test to simulate typing the letters hello into that entry. At that point, we can assert that the text inside the entry equals the string hello. That's pretty straightforward, but we can do something a little bit more complex. We can double tap in that space, again using the test utility. And in that case, what we would expect is that the selection has covered the text that the mouse was over at the time. And so we then check that the selected text is equal to hello, which it is, and also that the cursor has progressed to the end of the section that we were selecting. We do that by checking that it is 5. That's pretty straightforward. Of course, larger areas of functionality require larger unit tests, but that shows what is possible. And we've illustrated in the file listing there that there is a test file to match each of our code files. So the search screen has some tests and the welcome screen has some tests. And of course, naturally we drop them into our calculation code as well. But we can do more, and you might need to do more when you're testing graphical elements. So we've called this render testing. It's about validating that a component or section of your screen is rendering as expected. In the illustration here, I've made new test files that separate render testing from a regular unit test. So it's clear which that you're going to be finding in the file. So for each of our screens, we have a new file called render test. And these tests are able to execute normal unit tests, but also we can use that same test utility package to compare what our widgets are doing with a PNG graphic or an XML description golden file so that we know that the right thing has happened. To compare visually, we have assert image matches. That's going to use a PNG file to make sure that what has appeared on screen matches what you're expecting. And assert renders to markup is going to assert that the widget tree leading to the result is the same as you were expecting. So you can compare both what the user is seeing and the way that it's functioning, the state of the objects under the hood. Now, I say it's verifying what's on screen, but actually all of this unit testing happens in memory. We're using what's called a headless driver, and so you're not going to see this appear on your screen. You're not going to lose control of your mouse as it taps around inside the interface. So these are far less inconvenient, but also execute a lot faster than unit testing that you might have used in a web page or a Selenium driver, for example. In our illustration of files there, we have a new folder called test data. This is where we store the comparison files. We have a search for foo image, which I would imagine has the search widget set up. The word foo has been typed in and possibly enter has been hit or the search button activated. And also we're capturing the welcome start state in an XML file. But how did we create these? Do we really want to be manually creating all of these golden files? Well, no, that's not necessarily, thankfully. There will be a new folder created the first time you run these tests called test data failed. It's inside the test data folder, and it will contain the image or XML that was encountered that didn't match the expectation. So this is going to help you understand how something failed once your tests are running more frequently. But when they run for the first time, it's going to provide what did happen, and you can then move that into the test data folder if it's the right thing. So be sure to check the content. Visually, the PNG should be clear whether it's doing the right thing, and in the XML regard, a quick read through should clue you as to whether it is what you expected. And from there, in the test data folder, the next run will pass, and changes that were undesirable will again appear in the failed folder later on. So that's the different ways that we can test our code, but you should also use the Fyne app metadata file. It was mentioned earlier on, and here is the same illustration again. The reason this is important is because you could store metadata about your application in the repository, which leads to clearer conveying of that information, but also reproducible builds. You're not passing these parameters to build commands, forgetting one item, did I use the right icon or the right version number? So it all happens automatically, which also means you don't need to use build scripts. And this is a big plus. Go functions really well out of the box without anything like make files or scripts of any kind. And by integrating a metadata file, you can take your Fyne application from the first line of code through to delivering to your users without needing to script or add complicated parameters to anything. And it also leads to a smoother release process. You will perform a release. Any added information required will be asked, version numbers will be incremented, and your release will complete automatically. Much smoother than lots of command line parameters. Lastly, I wanted to touch on custom widgets. This is an area that perhaps raises many more questions. What's the right way to do things? How exactly should I be laying things out? So here I'm illustrating a creation of two new custom widgets, one called map and one called picker. They have their own test files and their render test files. You'll notice that we've created a new internal package called widgets. Now this is so that our application can use these reusable components anywhere in its code, but they're not readily available to outside scrutiny or usage. You could share this code by exporting its constructor and moving the widget package out of the internal area, or of course you could contribute it to a shared repository like FyneX, where people can around the world get use of your code. But for now we'll leave it in the internal place. Much like regular types in a file, we recommend only one custom widget per file. It makes it easier to discover and easier to debug when you're stepping around and seeing what's happening with more complicated behaviors. And you can see we've added our unit tests and we're validating the look and feel. And now we come to the design of an API for a widget. It's very important to expose as little as possible to publicize only behavior-based information for your widget, so that your users are not going to be confused by a huge number of different functions that might be available, thinking, what name would I give to an activity, and how would somebody interact with my widget to do that? And similarly, we store state, but we only expose or publicize the state that we want somebody to be able to interact with. So we might have some public state, we might have some internal private state, and here it's saying to store it only in your widget, because you don't really want it external to the widget, because then if you have two widgets, they're going to conflict. We'll talk about a widget renderer in a moment, and you don't want to put too much state into the renderer either, because the widget is the behavior, it's where the core state it should be. And touching on renderers, don't store a reference to your renderer. It's the widget's responsibility to create a new renderer so that it could be displayed, but this renderer can go away at runtime. It might be cleaned up through some memory requirements, or it might not be used for other, might be not needed anymore for other reason. And if you store a reference to it, you may get crashes through nil pointers, or you may just find that you're manipulating something that's not visible anymore, and you lead to a very complicated debug process, which ultimately was because it was an ill-advised thing to be doing. So let's look at a behavior-based API for a custom widget. First of all, we extend base widget, and we remember to call extend base widget in our constructor, and that's what allows the internal code in base widget to know the type of widget that it's behaving on behalf of. Export any fields that you want to be available through some sort of configuration, and create really helpful methods with good names that don't describe how a user might do something, but describe what it is that they're trying to achieve. And so here we have an illustration. Our new map widget is called map, and it's exposed. There's a capital M there so people can use it. We're extending base widget, and we have integrated here a watermark feature, so they will be able to pass what information should appear over their map. And internally, we're going to be tracking the zoom level and the XY coordinate. That's not something we want people to be able to write to or necessarily access directly, because that is internal to the state of our widget. It may relate to rendering, but we know that it matters to remember this information irrespective of whether it's visible or not, because that is the state that the user has put the widget into. We create a little constructor there, and we remember to call extend base widget. And lastly, we've created a new function called zoom in. I don't think that people would really expect a prize for guessing what that does. How it does it is hidden behind that comment zoom code, but we're performing whatever adjustments are necessary. And then we're calling refresh on our widget, and that's telling the base widget and the overall Fyne toolkit something has changed, we need to draw to screen again, but we don't need to know the details, so we just call that one function. Now that takes us to the renderer of a widget. We have, as I mentioned before, stored the main state in the widget, so we don't need to do that here, but we can store disposable information, caching information, something that helps the renderer indicate that it can be optimized based on some state that isn't the user state, but is relevant to how it's drawn on screen. We need to make sure in a renderer's refresh that we take any state that can be modified from the widget and apply it to our render state. And during layout, we need to be sure to adapt to the size that has been made available. A widget will always be bigger, or at least the same size, as its minimum size, which is declared in your code. You need to think what truly is a minimum size. We will always be bigger than that. Don't put something too big. Don't be encouraged to put a preferred size as your minimum, because then it's not going to function very well on small screens when you could truly have actually rendered, but you'd prefer larger. It's the job of a layout and a container to make your widget bigger as the space becomes available. And remember, because a renderer can be destroyed at any time, it's important that any heavy resources that you might have held on to get freed in the destroy method. We don't know, and there aren't guarantees about how frequently a widget will be created and a widget renderer will be created or destroyed. It's not going to happen very often, but it can happen, especially on more memory constrained devices. And so here's our map renderer. It's not a particularly exciting one. We just have a raster cache essentially, but we start by implementing the create renderer function on our map, which creates a new instance of this map renderer. We pass our widget, our map, into it, so it has a reference to our state, and we set up this raster for our cache. We also have a type assertion there to make sure that our widget renderer is truly a full widget renderer. This means that we get compile errors rather than runtime errors if we accidentally miss a method, typo, or if for some reason the interface definition changes. We then have our struct, which represents that data that we passed in. We're not doing anything in destroy because there's not a huge amount to do. That raster cache will be cleared up when our renderer goes away. Our layout is simply to set this cached raster to be the full size of our widget, and we have set the min size to 50/50. It's a little arbitrary in this case. If your widget was more based on textual content, you might want to measure each individual item and add them together. Now, the way that the renderer is conveying to the toolkit how to render is that we pass a list of objects back, and in our case, it's just this cache. And in refresh, I've omitted some code, which would of course draw the pixels of the map and overlay the watermark from our map widget. Now that's a lot of boilerplate, I suppose, to do something quite straightforward. And so we have introduced a new type called simple renderer in the widget package, which is really going to boost productivity for building trivial widgets, avoids creating a custom renderer completely, and where we returned a list of objects from our object method on the custom renderer, we just pass these objects into new simple renderer instead. We need to make sure that we apply any changes to the objects that we've passed through in our widgets refresh method, which will be called before the decision is made as to whether anything needs to be changed in the renderer. And because this is a default setup, the objects passed in will fill the space available because we're not controlling the layout anymore. So it's like the max container. Now, if we wanted to actually have a more complex layout with static items that were represented in a simple widget renderer, we could. We would then pass a container as the object that should be rendered and lay out the items inside that container like you would in any other setup. But isn't that a lot easier to understand than the boilerplate that was created? This is the entire replacement. The custom type wasn't needed at all. In the create renderer, we create a new cache if we need one, and when we pass back a new renderer that's going to lay out this cache. And you might notice it is slightly more efficient if the renderer is coming and going because we can reuse the same cache. But it does mean that the cache may be created sooner than in other cases. But roughly speaking, it is about the same memory utilization. And so there we have custom widgets as well. But before I go, I wanted to just leave you with a couple of thoughts. Export only what should be public, or export only what you want to support. You've put your code out there potentially as an open source project on a publicly available repository. If you have a public API, somebody might use it, and that would be great until you realize that then they don't want you to break it, because otherwise you'll get an open support ticket against a project that you thought was just a little bit of fun, or a widget that was used internally. You should document all of your APIs. This is not just for best practice because your boss said it would be a good idea, but it means that your IDE is going to be able to tell you about the function call that you're making. And if you need to go back to it, not only are your team potentially going to be happy that you've documented your code, but your future self also might be happy about it. Naming is tremendously important. Don't just put something there temporarily in the knowledge that you'll come back to it later, because who knows about later. Make sure that your API is clear. The smaller your function, the easier it is to write a good function definition or naming. It's always going to be simpler when the scope is small. Everything is clearer and you're going to have a really good idea about how something should function. Always better, I think, to have good naming than the documentation, because that way it's going to be a lot harder for it accidentally to do the wrong thing. It's right there in your code. But back to the beginning, start simple. Put together the minimum, get it working, and see how it goes from there, building on it slowly. Ask the community for help. As Gofi in this image here would tell you, the Go community is really welcoming and very helpful. Don't feel like you can't ask a question if you're just looking for a little bit of advice or guidance along the way. I hope that's been really helpful for folk to understand what we think are best practices when it comes to building Fyne applications on top of the Go programming language. I think we're out of time for questions on this topic, unfortunately, but do join us in the Q&A later and we will progress with our next topic in a moment.